Welcome back, everyone, from the coffee break. So before the break, we talked about the Fragile Families Challenge, and I told you a little bit about the scientific goals, and I told you about some of the results. Now you all are going to get a chance to do the same activity. So you're going to try to predict these same 6 outcomes using this birth cohort study. But now you all have a couple of advantages. So one advantage you have is that we've learned a lot from the participants already in the challenge, and we can tell you much more about what they've done. And we've also improved the metadata infrastructure as well. So I will tell you more about that. And so I'm going to now introduce the challenge, and then you all will get started. So again, the idea is we have these families, and we want to predict the holdout data, and you can use any approach that you want. So you can pick a small number of variables based on sociological theory. You can try to use all the variables and just put it into a machine learning model. You can look at the numbers yourself and try to somehow learn from the numbers without any statistical model. Whatever you want to do to predict what's in the holdout set, you can do that. Let me just tell you a little bit more about each of the outcome variables. Each of these is linked to a blog post. So if there's one, you can check out. If there's an outcome variable you want to learn more about, you can visit that blog post about it. In the interest of time, I would recommend that you all try to think about one outcome that you're most interested in, or perhaps focus only on the continuous outcomes or only on the binary outcomes. So first outcome is GPA. So we're interested in questions like, how do kids beat the odds academically? So here's the exact question on the survey. So there's often you want to know, if you're trying to actually predict something, you'll want to know exactly how the question was asked. Here it is. Basically, we get their kids' grades in 4 classes, and then we take the average of those. So here's the distribution of GPA and the training data. Okay, so I'm going to go through each of these pretty quickly. For the ones that you're most interested in, you'll want to go back and learn about them more. Yep?
When you say beat the odds academically, is that just mean get a high GPA?
It means getting a higher GPA than expected given all the stuff we know about the kid from birth to age 9.
So it would be like a 2-pronged thing of like figuring out what would be expected and then seeing like kids who are above what.
Exactly. So we think the machine learning is really good for helping us define as best as possible what is the best possible prediction given all the data we have for this particular kid. And then we can find the kids who do much different than what we expect in the best possible model. So the important thing here that we have the best possible model. So let's imagine that Sarah and Ian and Alex and I just decided to build this model ourselves and then tried to find the kids who are doing much better than were predicted in the model. You might say, well, how do we know those kids are really beating the odds? Maybe it's just because you all don't know about machine learning and you didn't build the right predictive model. So here, the idea that having everyone try the model and picking the best is a credible way of convincing people that we have something that's the best possible model or something reasonably close to the best possible model. So that's GPA. Grit is sometimes related to called perseverance or persistence. It's popularized in part by the research of Angela Duckworth. Supposedly, grit is more predictive of success than IQ. So here's an example where, again, grit is a predictor, but we are interested in where grit comes from. So which kinds of kids are particularly likely to be gritty and why. So there's a number of issues about measuring grit, which those of you who are psychologists I'm sure know about. This is the way that we measured it, which is a variation of the way that Angela Duckworth measured it. So again, not going to go through this in detail. If you're focused on grit, you'll definitely want to check out this and the blog post. Here's the distribution of grit. So let me describe a little bit about why I'm showing you these distributions. So you'll notice that this distribution is far skewed to the right. So most of the people in this survey are gritty by the measure we have. That's going to be important for how you think about trying to make these predictions. Material hardship, as I said before, this is a measure of experienced poverty. So we are interested in potentially why some people who look like they're not going to have a lot of material hardship have it, or likewise people who look like they are going to have it and don't have it. So material hardship is a series of 11 questions that are yes/no questions. So in the past 12 months, did you receive free food or meals? In the past 12 months, were you ever hungry but did not eat because you couldn't afford food, and so on. So we just take an average of these. This is the distribution of material hardship. So lower scores are better. Ideally, there would be no material hardship at all, but we do see some families that have some material hardship. But again, this is not a normal distribution, right? It has a distinctive shape. Eviction, this is about whether families are kicked out of their home. We're very interested, as I said, in does eviction cause worse outcomes as kids transition into adulthood? So we know that eviction is correlated with bad outcomes. I personally believe that eviction causes bad outcomes, but to show that scientifically is difficult because we don't have random assignment of evictions. Nor do we have random assignment of preventing evictions, which is something we could actually do. Often people say, oh, we can't ethically, assign people to evictions, and that is true, but we can randomly give people money, and so they'll be able to pay their rent. But as far as I know, that study has not been done. Anyway, so this, as I said again, also the causal inference questions turn out to be a little bit tricky, but for the purposes of eviction, here is the eviction question that we asked. And again, there are many different ways that people operationalize eviction. Those are actually important and subtle differences. So the NAs here are missing outcome data. We have a bunch of missing outcome data from people who dropped out of the study. You'll see the eviction rate, given the way that we've asked the question, is actually relatively low. There are techniques in machine learning that are specifically designed for when you have these imbalanced, they call it imbalanced training sets. So imagine if you were trying to tell the difference between a cat picture and a dog picture, and you had half cats and half dogs. That's one thing. But imagine if you had 90% dogs and 10% cats. That's a little bit of a harder thing for the machine learning models. So there are techniques that have been developed to try to address that. And some people in your group may know about those techniques. You may know about those techniques. If you don't, some people in your group may know about those techniques. Caregiver layoff, so this is about losing a job. And again, we're interested in potentially the causal effects of that on the caregiver and also the effects on the child. Here's a question about losing a job. Again, there are important differences in the way that this question is asked in the literature. So again, we have relatively low rates of layoff. Job training. Does job training obviously benefit the person who received it and also benefit the other people in the family? Here's the question as it's asked. Here's the training data. The distribution in the training data. So again, relatively rare, a lot of missing outcome data. So that's the training data, the outcomes. Oh, speak louder. Okay, so those are the outcomes. Now I'm going to introduce you to the predictors. Before I do that, though, I want to read this statement to you, which is one that we made all participants in the challenge read and sign. So the Fragile Family and Child Wellbeing Study is a data set of real people who have selflessly opened up their lives to us for the last 15 years so that their experiences can contribute to scientific research. By participating in the Fragile Families Challenge, you have become a collaborator in this project. It is of the utmost importance that you respect the families in the data by using what they have told us responsibly. So I want to just say now on a personal level, I had never been involved in a study like this before at all. And one of the things that I was incredibly impressed by was the amount of care that the entire research team took with the data and the amount of respect they had for the participants in these studies. Many of the researchers have been, they have followed these families since the kids were born. They did the first interviews in the hospital. These families have been incredibly generous with their time because they think it's important to help advance science. So when I did some of these dark matter interviews, This is one of the things that people told me is like, well, we think it's really important to understand what's happening in these families, and so we have chosen to participate. So I want us all to honor the trust that they have placed in us. So before you have access to the data, the files that you have now are currently encrypted. You will sign this data use agreement. After the activity is over, today, you will delete the data from your computer. If you want to keep working with the data, which is great, we want you to keep working with the data, you can reapply for access through the Fragile Families website. This will allow them to track the data access and make sure. So again, are there any questions about having the data? So you will get the data, you will sign this form, you will use it responsibly, and then you will delete it. Are there any questions or concerns about that? If anyone's not comfortable with that, they don't have to participate. And that applies also to everyone at the partner locations as well. Okay. So again, this is what the data looks like to a social scientist. This is what the data looks like to your computer. So after you type in the password to get access to the data, if you open it up in our studio, this is what you will see. It looks like a big spreadsheet of numbers. So if you try to put this into your favorite machine learning algorithm, it will not work very well. Not at all. And I want to start explaining to you why it will not work well. So as we've worked on this project, we think a lot about this kind of pipeline. I think we call it the research pipeline. So you start with the world and you do data collection. That gives you raw data. Then you take the raw data and you do some kind of data wrangling or data cleaning or data preparation, and that gives you the analytic data set. And then you do some kind of statistical modeling, and that gives you your results. So right now in the scientific field, there's tons of research about data collection. There's tons of research about, even more research about modeling and how we can do different kinds of statistical models. There's relatively little research and framework about this intermediate step, the data wrangling step. And so, but as we know, like a chain is only as strong as its weakest link. And so if you want to go from learning about the world to scientific results, you need to go through that intermediate step of data wrangling. And that is a step that you have to do before you start working with this raw data. If you just try to put this raw data into scikit-learn, it will not work. So we have, so what we observed during the challenge is that people struggled to do this intermediate step. And so what we have done is we have learned from all of the struggles of people in the challenge. They have generously shared their code with us. They have generously shared their experiences with us. And we have worked to try to make this data easier to use. So you will get to try that today. So how do I know what these variables are? So if you go to this website, you don't have to do it right now, but you can do it once that you start working. There will be a way for you to explore the variables. So if you have a question of, in the data file, it says Cm1 Ralph. What does Cm1 Ralph mean? You can go to this website. You may say, I'm interested to see all the variables that have been measured about mental health. You can go to this website and search for variables about mental health. So Cm1 Ralph, one of my favorite variables. It's actually a very important one. Cm1 Ralph is a constructed variable that measures the relationship between the mother and the father in the first wave of data collection. So what you'll see on the website, you'll also see certain tags about this data. So it was collected in the baseline wave. The respondent was the mother. It was a constructed variable, so let me explain what that means. That means the variable was not directly asked to the respondents. So what happens in the Fragile Families data, there are questions that are directly asked to the respondents, and then there are other variables that the research team thinks people will want to use that they create for them. They're called constructed variables. So this is often based on a number of different things in the survey, and sometimes based on information that you don't even have access to. Like they could look at the phone numbers and do things like that to try to construct these variables. And then what type of variable it is, ordered, categorical. Okay? Also down here are the different response values, which is also very important because you will see 4 in the data set, and you will probably want to know what 4 means. And in this case, 4 means the mother and father are friends. Okay? So you can filter the variables by topic or wave or respondent or variable type. Where does this name convention come from? So there is a pattern to these, the either constructed or non-constructed. If it's a constructed, it has a C. If it's not constructed, it doesn't. Then the next letter tells you the respondent. The next letter tells you the wave. And then afterwards, it tells you something about where the question is on the survey, if it's a non-constructed variable. So you don't need to understand this exactly, but you will often encounter variables and want to understand what they are. There is a logic to the naming convention. If you want direct access to the metadata without looking through the website, that's possible too. You can visit these, this website, or we have an R package, excuse me, an R package and a Python package which queries the metadata API to make it easy for you to look at the metadata without leaving your computing environment. You can also look to see the actual questionnaires on the Fragile Families website. So these are what the questionnaires look like. So as you build a submission, you'll want to, as I said, upload your predictions, your code, and a narrative explanation. Our submission platform does some checks before it allows a submission to be included. There are a number of bugs sometimes in uploading submissions. We have a whole blog post that helps deal with those bugs. And Alex has also created a template submission that you can modify to try to make it easier for you to be able to upload successfully. Then you can get on the leaderboard and see your score on the leaderboard set. So across all the locations during the Summer Institute, we'll all be using the same leaderboard. So you'll be seeing up there the scores, not just from people at your location, but from all the locations. So some advice that we have based on what we've seen. Most of the good approaches will involve careful data preparation and flexible models that avoid overfitting. So there's really, that second thing is really 2 parts. So I want to give you some advice based on what we've seen. So first, about the careful data preparation. So that is really about this step here, the step that we often don't usually talk about, but the step that is actually really, really important. So again, this is not going to work if you don't do this step. So let me just walk through a little bit about why this data preparation is so important. So, and this, what I'm going to talk about, for those of you who have worked with complex social surveys or longitudinal studies, this is very familiar to you. For those of you who haven't, what I'm going to describe is actually very common in complex surveys and longitudinal surveys. So here's a question that was asked to the father. I believe this is in wave 5, so this is when the kid is 9. Now I'd like to ask you some questions about your housing situation. Have you moved since the date of the last interview? Yes, no, refuse, don't know. So then there's something that's called a skip pattern. So depending on what the father says to that question, you will move to different parts of the survey. So if your idea is that everyone takes the same questionnaire, that's not true. It's more like a choose your own adventure story. And so that creates a lot of weird gaps in the data. So some of those gaps are created intentionally. So for example, if the father did not move in the past 4 years, then they don't want to re-ask all the same questions they asked before. That's a time-saving device. So then there's going to be blank information about where the father is living now. And the assumption is that you, as a researcher, are supposed to then go back to the old questions and pull that information in. That's what's called data cleaning or data preparation. So I'm just going to warn you, that's going to be really hard for you to do in the amount of time that you have. It's going to be really hard for you to do in any amount of time that you have, to be honest. But that is part of why there are all these gaps. Another thing is how many times have you moved since the last interview? This is a simple example of a question that would be skipped. If the father says no, I haven't moved, then we know this question gets skipped, but as researchers, we know the answer is 0. So you would have to then fill in this. If they have moved, you get a question like this. In your current housing situation, which best describes it? I rent my own apartment. I live with family or friends who rent, and I contribute to the rent. I live with family and friends who rent, but I don't pay rent. I own my house, and so on. And you see that this skips you to different parts of the instrument as well. Now I want to be clear, though, that this leads to a different kind of missing data. So if you say, I own my own house, this I believe is in the rent branch. How much do you think the house is worth today? How much do you think they own of the house? Whose name is on the mortgage of the house? So these are questions that only make sense if someone owns a house. But if someone reports that they are homeless, these questions get skipped, but they're not skipped in the same way that the answer is somewhere else in the data. They're skipped because they don't make any sense. If someone is homeless, it does not make sense to ask them how much their house is worth. And you could put in 0, but that is not necessarily right either, right? So that is a different kind of missing data. It's like structurally missing. And that is mixed in with the data that is missing that you could impute. And that's mixed in with the data that's missing because people don't answer. And that's mixed in with the data that's missing because people drop out. So this process is time consuming. This is an article from the New York Times, which also points out that even in non-survey data, data wrangling and data preparation is a huge amount of what data scientists do. I've seen this in industry as well. This is like most of what data scientists do at big tech companies is like prepare data. This process is error prone. So this is a paper that was published in the American Sociological Review, a correction to a paper. And then the person says, I made several errors related to the coding of missing data in my 2015 ASR article. I don't mean to pick on this person. There are many other examples I could have picked. But I want to be clear that what is happening right now is already error prone and incredibly frustrating. It is the worst, all this data cleaning. And so now imagine this times 1,000 or 100. Let's say times 100. So in a social science study, we might try to clean and prepare 10 variables. And that already has errors and problems. Now we want to clean and prepare 10,000 variables because we want to use all of the variables in the study. Just painful and not possible. So we think data preparation is a critical barrier to applying machine learning methods to complex data. And so we have tried to learn from what we did in the challenge. So for everyone who was in the challenge, we apologize. We did not know these problems were there. We have tried to learn from the pain that people had and the solutions that people developed to make it easier. So what if this data was as easy to use as your iPhone? So people who work with this data say, this data is complicated. We can't possibly make it that easy to use. And I would say it is very complicated, but so is the iPhone. The iPhone is very complicated, but people work very hard to make it easy to use. What if we did the same thing with survey data? And we think a key trick to that is going from human readable to machine actionable data. So we want to make the data easy to read, not just for people, but also for computers. And so, as I said, this is a big team effort. The key idea for us is that metadata is data. So we would never release data in paper files. We would never say, just download our PDF file and read it. That would never be how you would release data. And so if you think of metadata as data, then this is not the right format for metadata. So you can see this paper where we explain more about what we've done, how people in the challenge helped us think about this problem in a new way. So this is a picture showing you what the data will look like. So one row for each family, one column for each variable. The blue variables are non-missing, and the purple variables are missing. So this is what you are going to be facing.
This is like what would happen if we open.
Yep. And so those missings are coded as minus number, like -6, -9. So the missing values have different reasons. So -9 means not in wave. These are people who dropped out of the study. -6 is a valid skip. So this is related to the skip patterns. -2, don't know. -1, refuse. There's also some NAs. There's also some -3s. So I want to be clear, some of these were created by our privacy and ethics process. So we wanted to, one, minimize the risk, minimize the possibility of a re-identification attack, and then two, reduce the harm that would occur if an re-identification attack was successful. And so as part of that, we wiped out some of the variables because we thought it would add too much risk. I'd be happy to talk about that with people after the live stream is off. So oftentimes people try, during the challenge we saw people try to do a lot of complicated stuff to deal with the missing data in different ways. I was very, very surprised that it seemed not to matter. So in the special issue, there are papers that compare complex and simple approaches to dealing with the missing data, and they did not seem to find a difference. I was very surprised by that. So if you're interested in that, read the special issue when it's out. But given what these people have found, I would recommend that you don't spend a ton of time on dealing with the missing data now, unless that's something that's particularly interesting to you. So you'll also, in the data preparation, need to deal with unordered categorical variables. And so what I mean by that is they're data where the responses are categories. They're stored as numbers, but they're not really ordered numbers. So for example, whose name is on the mortgage of this house? Father's name only. Mother or current partner, both mother or father. People from the mother's family, people from the father's family. So it's not clear that like a 4 is twice what a 2 is here, right? So there are a lot of variables in the social sciences that are categories that are not ordered. So like my favorite is like, what's your favorite ice cream flavor? Like vanilla, chocolate, strawberry, mint chocolate chip. That would be stored as 1, 2, 3, 4. But you don't want to put that in your model as 1, 2, 3, 4, because that doesn't make sense. So one of the things people in the challenge struggled with is figuring out which variables were actually categorical, unordered categorical, and which were not. So let me give you an example of this. We came to the Fragile Families data team and said, okay, participants want to know which are categorical and which aren't. And the Fragile Families data team said, well, they can just look in the survey. And I was like, yeah, if there's 10 variables, they can definitely do that, and they'll want to do that. But if there's 10,000 variables, then that's really hard. So you will need to deal with this problem as well, but this problem will now be much easier thanks to what participants in the challenge have done. So several people developed heuristic approaches to try to decide whether something was categorical or continuous. They've shared those with us. We then had a member of our team go through and make a decision about every single variable and what type it was, and then put that into the machine-readable metadata. So now, if you want to know, is this variable, is Cm1 Ralph ordered categorical, that's one API call that you can make through the R package, and you will get the answer right back to you. Okay, so I had initially thought that, wow, people are going to do all these different things during the challenge, and it's true they did, but then when we stepped back, we saw there are really like a couple common things that everyone did. There's a couple common steps. What they did in each step was different, but there really are there is kind of a recipe. What people use for the vegetable in their recipe and what people use as the protein in their recipe and what people use as the sauce in their recipe varied, but there are some common elements. So I want to walk through briefly the common elements, and then in the special issue of SICSS, that we talk much more about these, and you'll get to see these in action in the papers. So the first step that all of the people did is data preparation. And now I'm going to tell you, I think the key ideas you'll need to deal with are missing data and unordered categorical. And here's a list of techniques that people used in their data preparation step. So one is they often did some kind of imputation using either the mean, median, or mode. Some people created missingness indicators. So after you do the imputation, you also add an indicator variable, whether it was missing or not. Some people did more sophisticated model-based imputation, more sophisticated than just doing the mean imputation. Some people did imputation based on survey structure. So again, remember I said that like certain things for the mother and the father, you might expect them to give a similar answer. You could do that, or you might expect people to give similar answers over time. Some people focused just on the constructed variables. Some people for their data preparation did a principal components analysis. So they wanted to create scales of variables. Some of those were interpretable. Some of those that come from PCA are not interpretable. One-hot encoding, so taking categorical variables and turning it into a series of dummy variables. Dummy variables is the social science way of describing this. One-hot encoding is the data science way. Standardization, so taking all the variables and converting them to be mean 0, standard deviation 1, which again would only make sense for continuous things, not so much for categorical things. And transformation, so taking square roots of variables, squaring them, logs, things like that. So I don't expect you to understand or do all of these things. I'm just going to run through these quickly so you have a sense of the range of things that people tried. Then the next step is choosing what variables you want to put into your learning procedure. So this is sometimes called feature selection or variable selection. And these approaches range from, I would say, more automatic to more manual. So the manual is like sitting, thinking, using expertise to try to decide. The automatic is putting them all in the model and letting the model try to select them for you. So the techniques that we saw people use are prior expertise, consulting the study documentation, doing a literature review. Also, sometimes people did this F-test. It's not described very well here, but what it is for each variable, univariate, saying, is this variable predictive of the outcome on a one-by-one basis? And then they would throw out all variables that weren't predictive of the outcome by themselves, and then try to focus on only things that seem to be related to the outcome. So this is a way of trying to get rid of variables. So let's give another way of thinking about this dichotomy. One dichotomy is you start with nothing in the model and you start adding variables as you go. Another approach is start with all the variables and try to get rid of variables. So this F-test approach and mutual information as another basically correlation between a predictor and an outcome is a way of saying we want to start with all, and then we'll start dropping variables that don't appear to be correlated with the outcome. Dropping low variance features is another approach. So if the variable doesn't have a lot of variability, let's imagine at an extreme, everyone gives the same answer for that predictor, then that can't be predictive, so you want to drop it. So for predictors that have low variability, people thought, well, that's not going to be very useful, so let's drop those. Sometimes people created multiple data sets using just the data from the mother or just the data from the father, things like that. Sometimes people created their own train test splits because they wanted to have an ability to train on some set, test on some before they would upload to the leaderboard. So once you've cleaned your data and picked the variables you want, then you use a statistical learning procedure. It's true that some learning and feature selection happen in the same model, but I think conceptually they're somewhat distinct. So the key ideas here are flexibility and overfitting, and those two are related. So some people used techniques from the general linear model. Some people used tree-based methods. So tree-based methods involve splitting the data into groups and then making the same prediction for everyone who's in the same group. So there's a lot of different ways that you could make these splits and then average over many trees. So random forest is one example, gradient boosted trees. The last approach, regularization approaches, what these are you can think of as taking a linear regression model, but then trying to penalize models that are too complicated. This is to avoid overfitting. So if you add lots and lots of variables in your model, you can do a good job of predicting the training data, but you'll potentially do a bad job of predicting the holdout data. And so what what Lasso does, or ElasticNet or Ridge, is they try to penalize complexity. So one way of thinking about what they, imagine you run a regression, you want to minimize the sum of the squared errors, subject to the constraint that your regression parameters the weights in your regression aren't too big. So you want to sort of shrink all of your weights to 0. This is a way of keeping the models to be not too much overfitting the training data and likely to work well in the holdout data. So what I just said in that minute is the subject of 20 years of research at least, many important theoretical results, a lot of practical know-how. To summarize that, though, it's generally good to put some kind of penalty on your model that's going to help you do better in out-of-sample prediction, even if you're doing worse in in-sample prediction. Like, that's kind of the paradoxical thing, is like, you want to do worse in-sample because that will help you do better out-of-sample. And again, this is something you can talk about with people in your team if you're not familiar with it. So those are some examples of what people did. You're welcome to try those techniques. You're welcome to try other techniques that people didn't use. That would be great too. Again, you'll need to upload submission, which includes predictions. So this is one prediction per family per outcome. So it's going to be a matrix that's 6 by 1591. A narrative explanation and the code. And this is the URL that you can use to upload to. And Alex has created a template file which you can download right here by clicking on this link. Before you go, I want to say one more thing. This is the number of submissions that did worse than the benchmark model. So the 4-variable linear regression model. And this is only submissions that beat the baseline. So we throw out all the submissions that did worse than the very simple baseline. Of those valid submissions, how many did better than a 4-variable linear regression? And the answer is most of them do not. So the point of this here I want to make is you can try a lot of complicated and fancy stuff, and that is great. But I want to remind you, it is quite difficult to beat a 4-variable linear regression. And I think this fact, I wish this fact was more well understood. So you might ask, why am I showing you this very dispiriting result right before you're about to go and try to do this? And the reason is because I want you all to realize that you can do very complicated and sophisticated and neat and exciting things, but if the goal is predictive performance, I want you to understand this is really hard. And I think if people understood how hard this was, policymakers would feel differently about using machine learning in a lot of high-stakes settings. So I want to be clear, this is difficult, and I want you to have that in your mind while you're participating. So good luck and enjoy. So what we're going to do now is we're going to shut off the live stream. Everyone here is going to sign this document. When you sign the document, we will tell you the password.